Today, let's talk about implementation of stack abstract data type using linked lists in C. We already covered the definition of stack as an abstract data type. To quickly recap, stack is a LIFO structure which stands for last in first out. It is a collection of items. There are operations like push, which insert element into the stack, pop, which removes elements from the stack, and this element is the most recently pushed element. We have operation of peek, or also called as stop, which returns the most recently inserted element. And we also have an isEmpty, which tells if the stack is empty or not. And we also can define a size function that returns the number of elements in the stack. Diagrammatically, stack can be defined as this structure where push would put element 1 on top of another. So you push 1, then 1 is put into the structure, and then pushing 2 would put 2 on top of 1. Pushing 3 would put 3 on top of 2, and so on. Popping would pop out the most recently pushed element. In this case, the most recently pushed element is 3, so 3 is removed. And pushing another element would put that element on top of the existing elements. This is a diagrammatic representation of the stack. Moving on, we also looked at the linked list data structure in C. To have a quick recap of the linked list structure, linked list contains a node which has two parts to it. The first part is the data, and the second part is a link which maps to the next element. And this structure can go on arbitrarily long till you find a node with no next pointer. And this linked list has a head pointer that points to the first element of the linked list. And for convenience sake, we also looked at how we also defined a list structure that contains the head pointer as one of the elements, so that we don't have to pass the double pointer to head to change head in functions that modify this linked list. So we also saw implementation of list using linked list in C. So we implemented list abstract data type using linked list in C. To recap the definition of list as an ADT, it is an ordered collection of elements. Each element is of the form t comma I, where t is of some type t. It can be also an abstract data type in its own right with its own operations and data model. And I is an ordinal, and this I, which is nothing but ordinal or the index, is used to order the elements of the list. So you can say which one is the first element, which one is the second element, and so on. We mapped this to the linked list in C to implement this list abstract data type in C. Some of the operations that we defined on list are insert, which insert element E at a given index inside the list, delete, which removes an element from the index given as input. You have size, which gives you the size of the list, number of elements present in the list. The isEmpty, which tells if the list is empty or not. These are the minimal set of operations that we had defined. We also had get element at index to return the element present at a given index from the list. We also have get index, which basically returned the index of a given element from the list. This is a quick recap of list ADT, and we implemented this list ADT using linked lists in C. So now what we're going to do in this video is to implement the stack ADT using linked lists in C. So to do that, what I'm going to do is to implement stack on top of the implementation of the list ADT using linked list. So we had already implemented list using linked list in C. So this implementation was for the list abstract data type. So this implemented functions like insert, delete, size, get element, get index, etc. It defined the data model in terms of the linked lists in C. What I'm going to do now is to implement the stack abstract data type. So this is the stack implementation. This is what we're going to take a look at. And this uses the list implementation that in turn uses the linked list. In the previous videos, we were also looking at how the stack implementation used list implementation using arrays in C. This is another implementation of list. This stack implementation using linked list is exactly similar to the stack implementation that we had that used the list implementation using arrays. There's no change, but then the underlying implementation of the list changed from the earlier arrays to the now linked list implementation. To make sure that we do it in a generic way, the stack implementation was just calling the API or contract defined by the list abstract data type. In the earlier example where we did a stack implementation using the list implementation backed by arrays, we physically copied code to the stack implementation. Even though we did not change anything in the list implementation, we physically copied the code of the list implementation and then called those functions from the stack implementation. But in this lecture, we're going to move a step ahead and use the list implementation backed by the linked list as a library from our stack implementation. So to illustrate the point, earlier lecture basically used a list implementation that used arrays, copied the code. So we copied the data structure which had an array in it along with the size and the method definitions to the stack implementation. But then we were just, from the stack implementation, we were just calling the methods that we copied. So we implemented push using the copied code of insert. So we called insert element 0L. We implemented pop in terms of delete 0,L and so on. So we physically copied the code. But in this case, in the implementation of stack backed by linked list, what we are going to do is to use the list implementation on top of linked list in C as a library, a C library, and just call the methods from our stack implementation. So the C library is compiled in C separately, generating a .o file, object file, and the stack implementation also would be compiled to its own .o file. And then this stack implementation would access methods, the insert and delete methods from this linked list implementation of the list abstract data type. So as we have seen earlier in the linked list implementation of list, we had a structure that something like this. So you had a list structure which pointed to a head, which eventually pointed to the linked list. So if you want to insert a new node, you would say, for instance, you have so this is the 0th node, this is the first node, the second node. So if I want to insert a node at the first position here, I would have to traverse through the linked list structure using a temporary pointer temp. I would go till the 0th node, and then I would do some pointer manipulation in such a way that the new nodes next point to the temps next, and then temps next would then point to the new node, and then this node would go off. This is how you insert a new node. It might also be the case that you want to insert the new node as the 0th node, in which case you would have to change the head pointer to point to the new node, and then new nodes next pointing to the old head. So in stack we would use this case always. So you always, when you're trying to push, you always insert your element at 0th position, and when you're popping, you will always delete the element at 0th position. Deleting would be a similar thing. So if you want to delete this node, you have a temp that is used to go to this node, and you have a previous node which points to the node before the temp, one node before the temp, and you would have to change the previous as next to temps next, and then delete this node. So if you want to remove the 0th node, you would have to again use two pointers, previous and temp. Previous would be kind of not used, to be null, and temp would point to the 0th node, and your head would have to point to the temps next, and then you basically delete the temp. So this is the implementation of linked list, which tries to realize a list abstract data type. For stack, the push method would always call the insert method on the linked list at 0th index always. So if you want to push one, so you basically have this new node that gets sandwiched between the head and the old 0th node. And if you want to, so this is the first node that's pushed, and if you want to, then these are all existing elements, so these existed before this node was pushed, so this is popped after this new node is popped. So if you want to push another node, same thing would happen. You would change your pointer of head to point to this new node. This new node's next would point to the old node at 0th index, and this thing goes on. So always we are trying to insert the element at the 0th index. So this new node, another new node coming in, which would again point to this. So this is a second, insert a third. Now if you try to pop, again you would pop from the 0th index always. So when you're popping, you basically remove this pointer of head and make it point to the removed nodes next, and this goes on. So this is basically pop. This is removed. Similarly, if you call pop again, this is removed, and so on. So now let's look at the code quickly. So we have a header file defined that has the data model defined for the list abstract data types implementation using linked list. So you have a structure which has a integer value, which is the data item, and then you have a next pointer to the next node, and then you have another structure defined which contains the head as one of the elements. I also added size to keep track of the size of the linked list. Makes it easier. This is the API of the list implemented using linked list. So you have size, first, last, obvious. Inserts an element at a given index. Delete removes an element from an index. Get index gets the index of an element. Get gets the element given an index. Append inserts elements at the end of the list. For stack implementation, we just use insert, delete, and size. And for peak or top methods implementation, we would use get. Okay, so this is the header file. This is implementation file. This file was reviewed in the last lecture. Nothing changed except I removed the main function here and then compile this as a library. Size just returns the size. First, last just does a get. Get is something similar. We kind of iterate through the linked list, go to the index and return the node's value. Insert, index check, iterate through the linked list, go to the place where we try to insert it, and then change the pointers appropriately. This was discussed in the last lecture. Delete as well, the same thing. Get index, can go to the node based on the value and then return the index, which is maintained in the counter that's incremented while we're traversing through the next pointers of all the nodes. And this is something that we've already seen. And now coming to the stack implementation, it's very, very, very simple. Your 4 methods: push calls lists insert method at index 0, pop calls lists delete method at index 0, top just calls the get element at index, which is represented as get here, gets the 0th node. isEmpty just gets the size and checks if it is equal to 0. If it's a 0, it returns a 1, and if it's a non-zero value, it just returns 0. So that's pretty much it. I mean, this is a very simple implementation. We have just relied on the list abstract data types implementation using a linked list to get our stack implemented. And the best part is we're just using the abstract data type as a library. So this code would work just fine, absolutely fine, if you replace the implementation with something else. So let's just run this code and see how the output would look like. What I'm trying to do in the code is, in the main function, I'm just inserting 1, 2, 3. I'm pushing 1, 2, 3, popping, and then trying to check isEmpty. After I pop 2 elements, this would return false or 0, and then I'm popping it again and then calling isEmpty again. So this would return 1 because I'm popping everything out, and the stack is empty at that point. So I just run it. I see push puts 1, push 2 puts 2 as well, push 3 puts 3, then pop would remove 3 because this is the most recently inserted or pushed element. So you have 2, 1, pop would remove 2, which was the next most recently inserted element. Pop would remove that, and then you have just 1 in the list. isEmpty would return 0 because it's an element. Then you pop it again, so your element is removed from the stack, and then when you call isEmpty, then you would get a true or 1. That's it, it's done. So in the next lecture, we would try to implement queue abstract data type using arrays. I would also implement the queue in the same manner by using the list abstract data types implementation that was backed by an array.